Hi guys, welcome to our new semester Mathematical Statistics 2 course. So on this one, we will focus on the interval estimation and hypothesis testing. So I believe you learn how to get the optimum estimators. What are the properties of best estimators? You all learned this from the previous class. So I believe we can go further and then see how we can construct the interval estimators and also how to construct an hypothesis testing. What are the optimum testing procedures? And also in the last part of the class, we will see the difference between the classical approach, frequentist approach, and the Bayesian approach. How to collect Bayesian estimators, very simple approach to get the confidence intervals for hypothesis testing using the Bayesian approach. So we will see those things. But before starting the interval estimation, I would like to talk about the location and scale parameters concept. So how can we understand the parameters, the location parameters, scale parameter, or shape parameter? And using this information, basically, we will construct one type of interval developing tool using the form of the parameters. So we will see that. So first of all, you have to identify the purpose of the parameters. Is it for the location, scale, or shape? Okay. Okay, so let me go. So I have to remember everything from the beginning. Okay, I believe we will not have a problem. Okay, so let's start with location and scale parameters. Last week we started with a little review of what we will need from the previous semester actually. Starting from the random variables concept, CGF concept, and also sufficiency, maximum likelihood estimator. We all reviewed that part. Very quick start. So you need to remember those things in this semester also. Okay, so let's start with location and scale parameters. Okay, so let's start with the location parameter first. Okay, so definition of a location parameter or location family of PDFs. Remember, we have many different types of families in statistics, family of PDFs. So here we have a similar thing for the location family, and similarly we have a scale family, and both location and scale family. Okay, so we have the PDF. This could be PMF also, okay? Be any PDF or PMF. So you know the difference between PDF and PMF, I believe. Then the family of PDFs, okay? Then the family of PDFs in this form, f of x minus mu. So x is a random variable. Here, mu is a parameter, okay? So if the form of the PDF is in this form, a random variable minus the parameter, okay? Indexed, we don't have any parameter. We assume that here. So indexed by parameter mu. Usually the range of mu for location case is minus infinity to infinity, but it depends on the distribution. So don't immediately write it this way. Okay, so make sure that is correct for your distribution. Okay, so code the location family of location family with standard PDF. So this is a textbook definition actually. PDF f of x. Okay, so if the form of the PDF is this one, f of x minus mu, then this family of PDF is known as a location family. Okay, and here mu is called the location parameter. So just look at the form of the PDF. If it is in this x minus mu format, then mu is a location parameter. It could be theta or any other parameter, but the form is x minus the parameter, whatever that is, called the location parameter for the family. Okay. So another definition here to be able to define the location parameters is the, oops, not this. Okay, so we have the location parameter here and location family of PDFs here. Okay, so then we can also say that our parameter, let's say it's mu, is a location parameter for the PDF f of x, okay, if and only if the distribution of x minus mu does not depend on mu. Okay, so this is a nice definition actually. So when we have a location parameters, then we can say that distribution of x minus mu will not depend on that parameter. Okay, so it will be independent of that parameter. Distribution of x minus mu will be independent of mu. So this is a nice property. So we will use this in different concepts. Okay, so remember this. So when we have a location parameter, then the distribution of x minus mu will not depend on that parameter. So to be able to show that our parameter is a location parameter, then only thing that you have to consider is a little transformation. Okay, so do a little transformation, y equals x minus mu. Okay, then since we know the distribution of x, okay, so keep x alone, like that. So on the PDF of x, replace x by y plus mu and multiply it with the Jacobian. Okay, remember. So what was the Jacobian? Dx over dy, how it changes. So this is kind of to adapt the ranges of or the domain of x to y. So in this case, it's just one, as you can see here. Okay, so and then show that. Also, you have to look at the range of the PDF. Don't forget to get that. So this will give us f of y with a range of y, okay? So this should be independent of mu. Okay, so using this type of very simple transformation, we can show that mu is a location parameter. So let's look at some simple examples that we are using a lot actually, so you know this form from very specific distributions. Let's focus on normal distribution, let's say, normal with mean mu and variance 1, let's say. Okay, so here we know that actually, if you consider the PDF, I believe you know the PDF form of the normal distribution. So when we consider the distribution of x here, remember we have 1 over square root 2 pi e to the minus x minus mu whole square divided by 2. So here the range of x is from in the real line, same for the mu. Okay, so if we focus on the form of the PDF here, so this is a function of x minus mu only, right? Okay, so this is a function of x minus mu. So it's a location family of PDF. And also, then we consider the distribution of x minus mu here. If mu is a location parameter, then the distribution of x minus mu should be independent from the mu, right? So, you know, for normal distributed random variables, when we have a linear combination of normal distributed random variables, it's also a normal distributed. Remember this property. So only thing that's changing it are the parameters. So we have a normal distributed random variable. So what is the mean of expected x minus mu? Expected x is mu, mu minus mu is 0. And the variance of x minus mu, mu is just constant. So variance of x is given as 1. Okay, so as you can see, this does not depend on any parameter in mu actually. Okay, so not depend on mu. So this means that here mu is a location parameter. Okay. Remember from the previous semester, we have a sufficient statistics, and the reverse of sufficient statistic was the ancillary statistic. So sufficient statistic gives us all possible information that is inside of the sample to be able to estimate the parameter. But the ancillary statistic, actually, distribution of ancillary statistic not depend on any parameter. So basically, it does not have any information related from the sample to be able to estimate the parameters. So actually, this helps us when we have a location family of PDFs. So this means that when we know that x minus mu is distribution of that one is independent of mu, so it will be an ancillary statistic for mu, right? We have mu term, but still we can use this type of information regarding the ancillary. So we have one theorem that help us. We will see that later. Okay, so we can use this information there actually. Okay, another example is a two-parameter exponential. Okay, so let's focus on exponential distribution, not two-parameter one. So let's see this theta as a location parameter or not. Okay, is theta a location parameter? So our question is this one. So to be able to do that, actually, when you look at the form of the exponential distribution, you will see that it's not in x minus theta form. But let's focus on the transformation again and then try to show that distribution of x minus theta is a function of theta or not. Okay, so if it is a function of theta, it's not a location parameter. If it is independent of theta, then it's a location parameter. So focus on this transformation here for the exponential distribution. So here x equals to y plus theta. Jacobian is the same. Okay, so for each case, actually, since we are doing the same transformation, this will be the same. And for exponential PDF, I believe you remember the exponential PDF. So we have 1 over theta e to the minus x over theta. What is our x? Now it is y over theta over theta. Okay, and when we consider the range of exponential is positive x greater than 0. Now x is y plus theta greater than 0. So here the range distribution depends on theta. So we cannot get rid of theta. Okay, so is a function of theta. So this means that here theta is not a location parameter. Okay, so basically when we have a location parameters, it shows us where many of the observations are accumulated, or which values of a random variable is most frequently appear. Okay, so basically when we change the location parameter, distribution automatically shifts. So let's say for normal distribution, let's say we have this normal distribution with mean 0. Okay, so let's say it doesn't look like a normal, but okay, so normal 0, 1. So let's say we shift the location to 2. Okay, so location directly shifts. So let's say this is normal 2, 1. So directly shift. So location, when we change the parameter value of the parameter, it automatically changes. Okay, so we have different concepts here. Like for a statistic, when we add some constant to our statistic, is it affected by this constant value, or the value of the statistic not changes? Okay, so we have two different concepts here. So let's first see location equivariance, and then we will see location invariance. So let's say we have x1 to xn. So this is a random sample. It doesn't actually have to be a random sample, but assume that it's a random sample. So this is not a necessary condition here. So let's say we have a distribution with PDF or PMF, whatever. Let's say it's given like that. Okay, mu is the unknown parameter, where let's say the range of mu is sigma. Okay, let's say we have an estimator to be able to estimate this unknown parameter mu. An estimator Tx. Since we are saying that it's estimated, it's a random variable, right? Remember, we have to use a capital letter here. So it is a function of sample random variables. Okay, so it's a random variable. Is defined to be a location equivariant. Okay, if and only if, when we add a constant, we can subtract that constant too. Doesn't matter. So let's say we have x1, x1 plus c. So we are adding the same constant to all random variables. If this equals to the statistic we have, exactly the same one, plus c. Okay, so if our estimator has this behavior, it is known as location equivariant. Okay, so this means that when we add a constant or when we subtract a constant, the value of the estimator shifts by c times. Okay, so sometimes we are doing some calculation, but let's say we have very large numbers and we don't want to work with very large numbers. Let's say we don't have a computer, we have just a calculator, and we don't want to, push lots of zeros and things. So we want to get rid of some parts. Let's say we reduce 1,000 from each observation that we have. So if you know that your estimator is a location equivariant estimator, what you have to do, then calculate whatever that you get actually from that reduction 1,000 value, and then add this 1,000 at the end to be able to get the exact value of the statistic that you have with your original data set. Okay. Okay, so we have for all x values, actually, and for all constant c. Okay, we have another definition for this Tx. Let's say our Tx is location invariant. So actually here the invariant means that when we add or subtract some constant value from each observation that we have in our statistic, so the value, the value of the statistic not changes. Okay, so location invariant. Okay, not change. If and only if. So when we add this constant to each observation we have or each random variable we have, we get exactly the same statistic value. Basically, this means that, so we remember the previous case, let's say we remove 1,000 from each observation that we have in our sample. So in this case, basically, we don't have to add any constants. So basically, when you subtract that quantity from your all observations and calculate the statistic, so it will give you exactly the same statistic that you will get without removing that constant from your observations. Okay, so your result will not change. So knowing this is actually helps us in many calculations. Again, for all X and C. Okay. Okay. Let's give some examples to location invariant and location equivariant cases. So then with the examples, you may see the whole picture better maybe. Let's consider sample mean, X bar. Okay. Location invariant or equivariant. Okay, so our statistic is X bar. X bar. Okay, so what is this, you know? X1 to Xn, so sum them up and divide by n. So let's consider the change one. So when we add a constant. Okay, so let's see what will happen. So we will have X1 plus C. Each observation, we are adding this constant over n. And at the end, what we will get, X bar plus T. So this means that X bar is location equivariant. So let's say you have a very big numbers and you don't want to work with those large numbers and get rid of a million or thousands. Okay, so when you calculate, when you remove that constant from each observation, and then if you want to calculate the sample mean, okay, calculate the sample mean from that reduced form, and then add this constant C, whatever that is, to be able to get the original statistic value. Okay, then you can get the value, original value of X bar. Oh, sorry, there should be a plus sign. Okay. And let's consider the sample variance. X1, xi minus X bar square over n minus 1. Okay, so let's say this is our T X1 to Xn. So let's see, it is location equivariant or invariant. So let's calculate X1 plus C till Xn plus C here. Okay, let's use the formula. So we have here for each xi, we are adding the C term. Actually, from previous one, we know that when we add a C term, so we will end up with X bar plus C term square, okay, divided by n minus 1. So these C terms will cancel each other, and we will exactly get the same S square value where we started. So basically, when we add a constant in the sample variance formula, we will get exactly the same variance. Okay, so this adding value will not affect our result. So S square is location invariant. Okay. Similarly, when you consider range, for example, range is also location invariant. So you can consider many different ones. Let's say also correlation coefficients. These are location invariant statistics. So when you add a constant or subtract a constant, the value of those will not change at the end. Okay, so let's focus on the let's focus on the scale parameter. Okay, so let's look at the definition of scale parameter. Okay. So again, let's say f of x var PDF or PNF. Then if for any sigma value which is positive, the family of PDFs in this form, 1 over sigma times f of x over sigma. So if your distribution is in this format, then is the scale parameter, scale family of PDFs, and sigma is a scale parameter. Okay, so just look at the form of the PDF, and if your PDF is in this format, then it's a scale family, and the parameter here, sigma, is a scale parameter. And similarly, like in the allocation parameter case, sigma is a scale parameter if and only if, when we consider the distribution of x over sigma, okay, as independent of sigma, okay. So if this is the case, sigma is a location parameter. Again, so this information helps us to get parameter-free distributions. Okay, so it will be important for us to get a parameter-free statistics at the end, because in many cases, you know, to be able to get the let's say p-values or the table values, we don't need to have these parameter values. So if we show that the distribution of x over sigma is independent of any parameter, but if we know the distribution with degrees of freedoms or other things, then we can use standard statistical tables to be able to define some probabilities actually. Okay, so this will be important for us. So let's look at exponential distribution again. Okay, exponential theta. So here let's try to find is theta location or scale parameter. So our question is this one. So let's look at the form of the distribution. So we have 1 over theta, e to the minus x over theta, x is positive, theta is positive. So when we look at the form of this PDF, so it's exactly the form of the PDF that is defined by a scale family, right? So our PDF is in this format. So exponential PDF is a scale family actually, family of PDFs. Okay, and when we consider a transformation, x over theta, okay, so if the distribution of this is independent of theta, then theta is a scale parameter. So our x is y times theta, Jacobian is just theta, dx over dy, and then when we consider f of y here, so 1 over theta, e to the minus 1 is x, it is y times theta over theta, multiply with the Jacobian. Okay, so we have e to the minus y, and when you consider the range of y, so x is y times theta greater than 0, so basically range of y is also independent of theta. So here the distribution of independent of theta. So this means that theta is a scale parameter. Okay. And similarly, we can consider uniform distribution. Uniform 0 theta. So it is a location or scale parameter. Okay, so let's look at the form of the distribution. So we have 1 over theta, okay? And the range of x is this one, remember. Okay, so we can define this one as x minus theta or x over theta. Since we have 1 over theta, like in the case of scale parameter 1 over theta times f of x over theta. So we don't have f of x over theta part right now, but when we look at the range, so basically if we define it like that, 0, x over theta 1, so it is in scale parameter, scale family of PDFs. And when we consider a distribution y over x over theta, so distribution of this will be uniform 0, 1. When you do the transformation, you will see that. So this one is independent of theta. So here, for this example, theta is a scale parameter. But be careful about this. Don't memorize it like that. Uniform distribution is always scale type and theta is a scale parameter. So the form of we have different forms of the uniform distribution. So be careful about the type of the PDF that you have. Let me try to remember the location type uniform distribution. Some form of the uniform distributions are location. Some parts like this one as a scale. Okay, so right now I don't remember any location parameter case. X over theta. Okay. Actually, when we do that, the range of this lower bound will be minus theta. So don't consider this one. Okay, so this part is correct one. So let me consider theta minus 1. Okay, so let's try this. I don't remember right now, but uniform theta and 1. Okay, let's write this. Okay, so we have 1 over 1 minus theta, and we have theta, x, and 1, let's say. Okay, so here theta is a location parameter or a scale parameter. So let's try to focus on that one. So basically here, when we divide theta both sides, so here it will be independent of theta, so it will be 1. We will have x over theta here, and here we will have 1 over theta. So it will depend on theta when we divide everything by theta here, so it will not work. Similarly, when we subtract theta from both sides, so the lower bound will be 0, so we will have x over theta, but the upper bound we will have 1 minus theta. Okay, so still we have a problem. So basically here, since we cannot locate it as scale or location, then it will define, it might define as a shape parameter actually. But for this case, let's, yeah, it seems like actually uniform distributions are very rectangular, so the shape of the distribution would not change with that one. Okay, so this type of distribution not exactly the same. Maybe we can say that by considering not y equals x over theta type transformation, but maybe 1 minus theta, 1 over 1 minus theta type transformation, we can get rid of that one. Maybe not exactly theta is a scale parameter, but 1 minus theta as a function of that might be a scale parameter in this case. So we have a question mark here for this example. Okay. Okay, so similarly, we can define our estimators as scale equivariant or scale invariant, like the previous location case. An estimator Tx based on a random sample, let's say, of size n is defined as a scale equivariant if and only if we if you multiply each x value by a constant, okay, not adding this time, but multiplying it, okay. So at the end, if we are getting c times tx, then we have a scale equivariant statistic for all x and c greater than 0. And similarly, we can define our statistic tx as a scale invariant if and only if, again, do the same thing, multiply each value by constant c. So it's exactly the same as the tx itself. So when we multiply our statistic, all observations with a constant, basically nothing changes, again, for each x and positive c values. Again, we can do the calculation for known estimators like sample mean and for others. So let's focus on the sample mean, x bar. So let's say our tx equals x bar. Okay, so then let's calculate c times x in this case. So we have c times x1, blah, blah, c times xn over n. So we will have x bar plus c, right? Oh, sorry, not x bar plus multiplied by c. Okay, so basically, sample mean is also scale equivariant. So it is location equivariant and also scale equivariant. When we consider the standard deviation, let's think about the form of the sample variance. So we have in summation xi minus x bar whole squares. So x bar is c times x bar. So each xi will be multiplied by c. So at the end, we will get c times s squared. So here the sample variance also scale equivariance, not invariant like in location case. So basically, when we multiply each value with some constant, the statistic itself multiplied by that constant. Okay, but we can consider some examples like some statistics like x1 plus x1 over 2 or x1 square over summation xi square. So when basically we have the ratio of two statistics, these constants will disappear. Okay, so if you have these type of correlation coefficients again, so these are scale invariant statistics. Okay, then we can combine these two like in normal distribution case. Okay, let's say we have two parameters in our distribution. Then we don't know which one is a location, which one is a scale, or do we have a different type of distributions? Okay. Okay, so again, let's say f of x be any PDF or PMF for us, and then for any mu in the parameter space, and also sigma greater than 0 case, then the family of PDF 1 over sigma f of x minus mu divided by sigma is a location scale family. Location scale family of PDFs. Okay, and then here mu is a location parameter, and sigma or sigma square, sometimes we are using that, is a scale parameter. So when we have two parameters, so if our PDF is in this format, okay, so sigma is a scale parameter and mu is the location parameter. So by just looking at the form of PDF, so you can guess what type of PDF you have. Okay, so actually when we have okay, so let's combine the things with the transformation again, like in the previous cases. So mu, actually we are considering just one transformation, not two transformations for each parameter. So if mu is a location parameter, and let's say sigma is a scale parameter. Okay, and with this PDF, okay, if let's say for this PDF, let me also say that if and only if the distribution of x minus mu over sigma. So let's consider just this transformation. If this transformation gives us a distribution independent of mu and sigma, so mu is a location parameter and sigma is a scale parameter. Okay, is independent of mu and sigma, or sigma square. Sometimes we use that. Very simple examples that we have is a normal distribution. So when we have x normally distributed with these two parameters, mu and sigma square, as you can see, let's write the PDF form of this. Okay, so we have 1 over 2 pi in square root and sigma, 1 over sigma here, this quantity, and then e to the minus, okay. Okay, so we can write this way, x minus mu over sigma whole square multiplied with 1 over 2. Okay, so the range of x is this one, range of mu is this one, sigma square or sigma is greater than 0. Okay, so this is in this form, right? And also when we consider the distribution of x minus mu over sigma, okay, using the property of normal distribution, this is standard normal. And distribution is independent of mu and sigma or sigma square, okay? So this means that mu is a location parameter, sigma is a scale parameter in this case. Or let's look at a Cauchy example. So let's say we have a Cauchy distributed variable theta and mu, let's say, and then when we consider the form of the PDF here, okay, so 1 over theta pi, okay, so we have 1 plus x minus mu over theta whole square, okay, so the range of x is this one, range of mu is the same, and theta is positive. So again, when we look at the form of this PDF, it is in this form, right? Like location scale family type. And also when we do the transformation, okay, so x minus mu over theta transformation here, okay? So you will get that we have theta terms cancels out from the Jacobian. So we will have Cauchy 0, 1 case, 1 plus y squared. Okay, so it's independent of nu. So nu is a location parameter, and the theta value. So theta is a scale parameter here. Okay. Okay. So basically here, from this example, you can see that these parameters. Okay. So nu here as a location parameter. Theta is a scale parameter, but actually these are not exactly the mean term and the variance term all the time. For Cauchy distribution, remember we don't have any moments exist. So moments, first moment gives us the mean. So by the second central moment, we can get the variance. But for Cauchy distribution, we cannot find it. They are not exist actually. They do not exist. But we can relate this with the measure of location and measure of scale, not directly relate with them the mean and the variance, okay? So you have to think them as the measure of location, okay? So this one is a measure of location, and this one is a measure of scale. Although they are not related with the sample mean or the population mean or the population variance or sample variance, okay? So with this concept, you can see that. And also we can talk about the location scale equivariance, or actually we are not use equivariance that much for this concept, but location scale invariance statistics. So for this case, actually, these are very helpful to be able to define some test statistics actually. Again, by using distribution-free statistics, if we know that if the distribution of a statistic that we are using is independent from the parameters, then we can use standard statistical table. So in this context, actually, being location scale invariant will be helpful. Okay, so let's say again we have a statistic Tx1, Txn, a statistic. Here, when we consider the location scale type cases, so here, remember for location invariance or location equivariance, we were adding some constants to each observation, and for the scale invariance or equivariance, we were multiplying by constant. So for this case, we combine each. So we multiply each value by C, okay, and then add a constant D, let's say, okay. So do the same thing for all observations that we have. Okay, so if we do that, and if we are getting exactly the same statistic we have, okay, so we multiply each value by some constant and add a constant, and the value of the statistic not change. Okay, so it's very nice property actually. So here for all x positive, C and real D. Okay, then this means that the statistic here Tx is a location scale invariant statistic. Actually, this means that distribution of Tx is independent of location and scale parameters, whatever those are. Okay. Okay, so one example can be xi minus x bar over s, or maximum minus minimum over S. Okay, so these are some location scale invariant statistics. Okay. Okay. So we have also Pitman estimators. Okay, so today I will cover also the Pitman estimators, and then I will finish this part. Okay. Or maybe give also the Bassett theorem and statistics, and then we stop where we will start the interval estimation. Okay, so let's do that. Okay, so let me choose a different color. Which color? Okay, so this fuchsia. Okay, so Pitman estimators. So Pitman estimators actually helps us to generate an estimator which gives us location equivariant or scale equivariant estimators. Okay, so at the end of these, we can generate, we know that the estimator that we observe as location equivariant. Okay, so for the location, we have two different types, for location parameter and for scale parameter. And basically, we have a formula for that one. So it's not special, actually. So we have a Pitman estimator formula. So when you apply that, and resulting estimator will be location equivariant. Okay, and it will have most of the cases, they have some special properties. Okay, so for location parameter. So usually in my exams, I don't ask questions from this because it's like memorizing some sort of formulas. So if you apply that, you will get the result. Okay, so let's say, let me use a different color now. Purple. Okay, let's x1 till xn. Let's put a 3 dot here. Mathematical dots. B, a random sample, okay, from some known PDF. Given PDF where theta is a location parameter. By the way, so we learned that how to detect a location parameter, how to detect a scale parameter. So basically, when you have a parameter where you cannot define it as a location or a scale parameter, okay? So then this means that it will be a shape parameter, okay? So when you do a transformation like y equals to x minus theta, and then distribution of y not independent of theta, let's say, or do this after that. Okay, so it's not location parameter, you decide, and then let's try, is it a scale parameter or not? Then do the transformation y equals x over theta, and if you are getting that distribution of x over theta also not independent from the theta. Okay, so it also still depends on theta. So it's not a location parameter, it's not a shape parameter, a scale parameter, sorry. Then the rest is the scale parameter. So we have the third option. So basically, to be able to show that there is a parameter is a shape parameter, then you have to show that it is not a location parameter and it's not a scale parameter. Okay, so if these two not handled, if you cannot prove those two, then our parameter will be a shape parameter. Okay, so let's continue with this one. And I remember that I forgot to tell you. So the estimator defined as, okay, so we have a formula here for this. So we have a vector of random variables. Okay, so we have a ratio. So we have integral from lower bound. Okay, so this is a range for theta, not a random variable x. Okay, so it's a function of tx, as you can see. So it should be a function of x. So we don't have a, so this is an estimator. It cannot contain any unknown parameters. Okay, so use the lower bound of the range of theta till the upper bound of theta. Okay, so theta times the joint PDF actually of PDFs. So here's, let me write the joint PDF, but since we have a random sample, this is the multiplication of marginal PDFs, okay? D theta, not X, okay? And then do the same thing here from lower bound of theta to upper bound of theta. So this is general definition and the PDF here. So if you do it for X actually, so all X values, then we will end up with 1, but we have just one theta value here. Okay, so just one integral. Okay, so this is known as the Pitman estimator of location or theta. Okay, and this estimator is a location equivariant estimator, okay, with the smallest mean square error. What this means? Okay, smallest. So what is mean square error? Do you remember from the previous semester how we calculate the mean square error? So we have a parameter and also an estimator. Expected difference between these two, square difference actually. So let's say mean square error. So expected value of the statistic we have, let's say, minus the parameter itself, get the square term. Okay, so this is the mean square error. So when we have the smallest mean square error, this means that the statistic we have is very close to the original parameter value. So this is a very nice property actually. So what we want, so it gives us kind of a best estimated that we have, right? This includes the the bias term and also the variance term. So we have the lowest bias and lowest variance terms here as a result of this calculation. Okay, so this will be a function of a sufficient statistic. Okay, so this is a nice, this gives us a nice property, the estimator with a nice property. Let's look at some examples how we can calculate this. It's very simple actually. Just apply the formula. And here, don't remember to, we are integrating this integral with respect to theta. So we have to find the range of the parameters here. So it's very important. So you will see actually how we get the result. So here, this is a show that example, but without a show that question or example, you can get the results. So here, show that if X distributed as uniform with these parameters, theta minus 1/2, and this one here, so this will give us a, this theta is the location parameters. Okay, then I couldn't get an example 10 minutes ago. Okay, so this is the minimum order statistic plus the maximum order statistic over 2. Okay, so we will show that this is our Pitman estimator here is in this form. Okay, okay, so here actually, so you can show that theta is a location parameter. How we can do that? Okay, so here let's consider the PDF f of x theta. So what we will have here, okay, so we have one only as a PDF, Okay, so, and when we look at the range of x values, we get this, theta plus 1 over 2. Okay, so subtracting theta from both sides, basically we will get minus 1 over 2, x minus theta, and 1 over 2. So as you can see, this is a function of x minus theta. Okay, so this means that we have a location family of PDFs, and when we consider transformation here, so we will see that this is uniform, minus 1 over 2 to 1 over 2 actually independent of parameters. Okay, so theta is a location parameter. So with this one, so you can show we have a location parameter. So then we can use a formula for the Pitman estimator for location parameter. Okay, so okay, so we need a range for theta. Okay, so what is the range of theta? So we know the range of x. It depends on theta. So using the range of x, basically we can define a range of parameters for the joint distributions. So okay, so let's write our PDF again. So we have this theta plus 1 over 2, and let's try to join PDF. So for a random sample, you know, this is the multiplication of all ones, marginal distributions. But when we consider the range here, for each xi value, we don't have the, okay, I didn't write the equality, don't put that, 1 over 2. Okay, so now our main aim is to be able to define the range of theta, okay? Because in the formula, remember, for the Pitman estimator, we need to integrate for theta. So in the integral, we need to use the range of theta. Okay, so what is the range of theta? So here, again, as usual, we are using the order statistics. So for each xi is in this range, so this means that basically when we order them from smallest to the largest one, so they will be inside of this range, okay? So using this logic, so we can put equalities maybe here. So theta plus 1 over 2 and theta minus 1 over 2. And from this part, we can get an upper bound for theta. And using this one, we can get a lower bound for theta. So combining this and writing theta alone, so what we have? So upper bound, so we have theta in the middle. Okay, so from the lower bound x1, so we have x1 plus 1 over 2 as an upper bound for theta. And as a lower bound here, when we make theta alone, so we have the maximum minus 1 over 2. Okay, so now we define the range for theta when we have a sample. Okay, we don't have to put an equality sign actually. So I didn't. If you want, you can put it, but if you are using equality sign, so then put it everywhere. Okay, so then apply the formula for the Pitman estimator. Okay, so from upper bound to lower bound. Let me. All right. Okay, so here. Okay, so lower bound is, let me put a capital letter, 1 over 2. This is the lower bound for the integral, and this is the upper bound for the integral. Is it plus? Yeah, is it plus? Join PDF, so we have the theta and the join PDF. Join PDF is just 1, so I don't want to write it. And similarly, we have the same ranges. Lower maximum minus 1 over 2, minimum plus 1 over 2. Join PDF is just 1 d theta. Okay, so then we integrate it basically. What we will get, so here we will have theta square over 2, and writing the upper and lower bounds inside of the formula. So we will have 1 over 2. Okay, so we have x1 plus 1 over 2 whole square minus xn minus 1 over 2 whole square. And in the denominator, we will have x1 plus 1 over 2 minus xn minus 1 over 2. Okay, so these are cancelled each other, and what we will get is x1 plus xn over 2. So actually we showed that we have this Pitman estimator. Basically, when we add a constant to each statistic we have, each random variable, sorry, these are all should be capital letters, not lower cases. Sorry about that. So this should be a capital S, this should be a capital X. So this is an estimator at the end again. Okay, so when we add a constant here, so basically, we will end up with Tx plus X, right? Or C, sorry. So when we add C to each variable here, so we will end up with the location equivariance statistic. Okay, so as you can see. Okay, so similarly, we can do the same thing for the scale parameter, but the calculation is a bit different. Just the formula is different for scale parameter. Okay, so again, we have a random sample. We assume that we have a random sample. A random sample from some distribution PDF where theta is positive here. Where theta is a scale parameter, is a scale parameter. Okay, and within the class of scale equivariant estimators. Within the class of scale equivariant estimators. An estimator Tx. Okay, calculated with this formula. Okay, so from 0 to infinity. Again, we are integrated with respect to theta parameter. Okay, so not x. 1 over theta square and the joint PDF. X and theta d theta. And do the same thing here. 1 over theta cube and the joint PDF. X and theta d theta. This will give us a scale equivariant estimate. Okay, so so we will end up with this statistic times that constant. So this is Pitman estimator for a scale parameter theta. Okay. And basically, we will see this risk concept later, but as a result of this, basically, we will get a uniformly smallest risk for the, so for given certain loss function. So I will skip that. So this will be again a function of a sufficient statistic for theta. Okay. So let's do an example. So let's say we have a random variable which is uniformly distributed with these parameters. So we showed that actually this theta is a scale parameter before today. So again, we need the range of theta to be able to find a Pitman estimator. So we will use the same logic here. For uniform distribution, remember the range of x is this one. So for the joint distributions here, x1 to xn, when we consider joint distribution, f of xi, oops, not f of xi, sorry, x1 to xn theta. So we will have 1 over theta to the n, and for each xi value is in this one. So this means that basically, since each xi value is in this range, then from 0, the smallest, to the maximum 1 should be inside of this range. Okay, so with this actually we can get the lower bound for theta. Okay, so we need to range for theta. So from this case, we can get the range of theta for a random sample. Then we can calculate the Pitman estimated for a scale. Okay, so from nth order statistic to infinity. 1 over theta square and 1 over theta to the n d theta over the same 1 over theta cube 1 over theta to the n d theta. Okay, so as a result of that, it's a simple integration actually. So we ended up with n plus 2, n plus 1, and the nth order statistic here. As you can see, when we multiply this by a constant, basically the statistic will be multiplied by a constant. So it's a scale equivariant statistic. Okay. Okay, so let's stop here today. So I will continue with the Basel theorem and independence of the complex sufficient statistics and also the ancillary statistics next class. So I will start with these, and then we will go to our main topic, interval estimation. So we will be focused on the interval estimators or estimation part for a few weeks actually before the hypothesis testing part. Okay, so see you in the class, guys. So in the first weeks, I cannot, arrange my time that well. So after a few weeks, 1 or 2 weeks later, then I do everything arranged. So I couldn't record the class earlier this week. So I'm planning to do that on Friday, but I couldn't. Sorry, I was a bit late to record the class. So see you in the class on Wednesday, okay? Let me go to the Zoom and stop sharing and stop recording. So see you, bye-bye.